In science, we often work hard to prove our ideas true, but just because something hasn't been proven yet doesn't mean it isn't real. Consider black holes. The possibility of black holes was seen within Einstein's theory of general relativity back in 1916. Using older Newtonian physics, their existence was suggested even earlier, in 1783. That means for over a century using relativity, or nearly 2 centuries using Newton's ideas, black holes were a theoretical possibility before we ever saw one. The first confirmed black hole, Cygnus X-1, wasn't identified until 1971. Since it happened once, it's reasonable to think it could happen again. In the vast ocean of scientific ideas, there could be exotic stars and strange forms of matter that are predicted but remain unseen. What are these objects? We don't know yet. That's why they're unproven. This exploration will look at some of the strangest objects or states the universe might contain, if only we could find one to be sure. Check back in a couple hundred years to see how many turned out to be real. For astronomers, stars are a natural starting point. Stars are among the most beautiful and inspiring objects in the cosmos. Through powerful thermonuclear reactions, they emit immense light, illuminating the night and warming nearby planets. Through mergers and explosions, they also create the heavy elements that make up much of the matter around us. We've come a long way in understanding stars, even predicting when our sun will run out of fuel. But today, we're not discussing familiar stars. Instead, we'll consider stars we've never seen, ones that physicists say could exist hypothetically, including stars literally made of vacuum. First, we need some groundwork on how stars work, starting with our sun. The sun is made of gas and plasma, not solid matter, so you couldn't stand on it. Gravity pulls everything toward its center. So why doesn't the surface gas collapse inward? There's an outward pressure from the core that balances gravity's pull. This pressure mainly comes from radiation produced by fusion reactions, the same radiation carrying light and heat to Earth. Whether you think of radiation as photons or waves, its journey from the core outward creates a push in all directions. This pressure isn't enough to stop you from falling in, but it's sufficient to keep the sun's own relatively light gas from collapsing. This balance between inward gravity and outward pressure is a feature of almost all known stars. What distinguishes star types is the source of that pressure. For our sun, pressure comes from fusing hydrogen into helium. In about 5 billion years, when the hydrogen is depleted, the sun will become a red giant, generating pressure by fusing helium into carbon and oxygen. Eventually, it will run out of these lighter fuels. It will then collapse into a small star called a white dwarf. With no more fusion, white dwarfs are sometimes called stellar remnants. But without fusion, what provides the supporting pressure? Gravity compresses the white dwarf's gas until it's so dense a new pressure emerges, called electron degeneracy pressure. This is a quantum effect, the same one preventing your hand from passing through solid objects. Electrons simply cannot get too close together without enormous energy. Some stellar remnants are so massive that even electron degeneracy pressure can't counter gravity. This limit is called the Chandrasekhar limit. No stable white dwarf can be heavier than about 1.4 times the sun's mass. If a star's core is heavier than this after burning all its fuel, it will collapse further until an even stronger quantum pressure appears, known as neutron degeneracy pressure, which prevents neutrons from getting too close. A star reaching this state is a neutron star, the smallest and densest known stellar objects. You might wonder if there's a maximum mass for a neutron star supported by this pressure. There is, around 2.2 solar masses. Anything heavier would keep collapsing under its own gravity. As far as we know, neutron degeneracy pressure is the strongest ordinary matter can exert, so nothing would stop a sufficiently heavy remnant from collapsing indefinitely. This fate may await the most massive stars we observe. From outside, these stars would become so dense all we'd see is a black hole. Scientists then wondered, what about a star not made of ordinary matter? If exotic matter could produce even greater pressures than neutron degeneracy, what new stars could exist? You might think we could continue the pattern. Stars could get even smaller and denser than neutron stars, supported by some greater pressure. You might think the only limit is the point of no return where they become black holes, when a star becomes smaller than its Schwarzschild radius. That's almost true. Physicist Hans Adolf Buchdahl showed in 1959 that a star made of any realistic matter, with positive energy density and pressure, can't be smaller than 9/8 of its Schwarzschild radius. That factor means any realistic star must be noticeably larger than a black hole, making them easier to distinguish. That's when physicists began asking about less realistic stars. What if a star was made of matter, allowing pressure to be negative in some regions and positive in others? Then Buchdahl's limit wouldn't apply, and that star could be less than 9/8 of its Schwarzschild radius. In fact, it could be almost the size of a black hole with the same mass. Such theoretical stars mimicking black holes became a nuisance for astrophysicists. Every time they discovered something thought to be a black hole, they had to qualify it might be an extremely compact object instead, though most were convinced it was a black hole. But back to the main point, what would these exotic stars with negative pressures look like? The answer is stranger than you might guess. Tolman, Oppenheimer, and Volkov derived an equation in the 1930s describing how pressure changes in a stable star from its center outward, now called the TOV equation. If a star's center has significantly negative pressure, exerting an attractive pull instead of a push, the TOV equation says this star can only be stable if its pressure does something very odd. First, the pressure must blow up to negative infinity somewhere inside the star. Then, it must flip sign to positive infinity and decrease outward until reaching zero pressure at the star's surface. The location of this infinite pressure depends on the central pressure. Tune that central pressure just right, and you can keep the pressure finite right up to the star's edge. This happens when the central pressure exactly equals and opposes the star's energy density there. In this special case, the TOV equations say pressure and energy density remain constant, equal, and opposite throughout the entire star, up to its surface. If you've seen other discussions, this might sound familiar. A constant positive energy density paired with a constant negative pressure doesn't sound like any known star, but it sounds like a mysterious component of our universe, dark energy. Since the pressure and energy density in such a star are equal in magnitude, it's not just any dark energy. Those are the exact properties of vacuum energy. This exotic star came to be known as a gravitational vacuum star, or Gravastar for short. Inside a Gravastar, there is precisely zero gravitational force because the positive energy and negative pressure exert a pull and push that cancel each other out. Since the pressure is constant, there's no pressure gradient to push in any direction either. If you were inside a Gravastar, you would neither be pulled in nor pushed out. You could float freely as in a real vacuum. Another curious feature of stars with negative pressures is that the closer they get to the Gravastar limit, where the infinite pressure surface reaches the star's edge, the more their size approaches that of a black hole of the same mass. This raises two key questions getting recent attention. First, how can we tell if the extremely compact objects astronomers see in merger events and galaxy centers are black holes or exotic stars of nearly the same size? Second, if Gravastars are real and scattered throughout the universe, could they be the dark energy causing the universe's acceleration for the past 5 billion years? To answer the first, physicists rely on the main distinction. The event horizon, a black hole's defining feature, is that nothing falling inside or touching its surface can ever escape. If an exotic star is even slightly larger than its Schwarzschild radius, it wouldn't have an event horizon and could potentially emit light outward. Objects without event horizons could also have different gravitational wave signatures during mergers than black holes, allowing us to tell them apart using observatories like LIGO. But even with these tests, sufficiently small, dense stars can still be hard to distinguish from black holes. So far, the best we can say is that black hole candidates have a radius approximately equal to their Schwarzschild radius. In some cases, that's a rough estimate, but in others, we've calculated it with extreme precision. As for dark energy, things get heated. In early 2023, An analysis led by physicists at the University of Hawaii found astronomical observations of massive black holes showing them growing in mass over time, at the same rate dark energy would be expected to grow due to universal expansion. They concluded black holes must be made of dark energy and are more like gravastars than ordinary black holes with infinite density singularities. This conclusion was fiercely contested. Astronomers argued the observational data analysis wasn't quite right, and theoretical physicists argued universal expansion should have nothing to do with black hole growth. So while the idea dark energy could exist as gravastars sounds exciting, the scientific community likely won't be convinced without better data and more compelling theoretical models. So while gravastars may exist, we're far from proving them, and they might look too much like black holes to spot easily. But the next exotic object explored today should be as distinct from a black hole as possible. They are black holes' opposites, the push to a black hole's pull. They are white holes, and there's no reason in physics why they couldn't exist. Start with a simple analogy. Imagine a cone. You probably think of something pointing up, like a traffic cone, or down, like an ice cream cone. These are cones in the real world. But if you write the most general mathematical equation for a cone and graph it, you get something looking like two cones glued together. A mathematical cone has two halves, one pointing up and one down, connected at their tips. Real-world cones are just chopped-up pieces of the full mathematical cone. Black holes are the same. Many black holes we see are remnants of massive stars whose extreme gravity caused collapse. Once created, a black hole is permanently separated from the world around it by a spherical barrier called the event horizon. Anything can fall in, but nothing, not even light, can come out. This spacetime structure can be summarized in a Penrose diagram, a way to represent infinite spacetime in a finite drawing. Its key feature is light travels upward at 45-degree angles, making it easy to see where light can or cannot go. In this diagram, region 1 is the regular universe, containing the original star before it became a black hole and everything outside it, from the infinite past to the infinite future. Region 2 is the black hole, separated by its event horizon. You can see light easily enters the black hole but cannot exit. It inevitably hits the singularity. The same holds for ordinary matter, moving slower than light, traveling upward at steeper angles. This diagram accounts for black hole formation at a specific time when the star collapsed. In the far past, there was no event horizon or black hole. Light could travel freely. While this diagram represents black holes we're used to, it's only one piece of the full mathematical description in general relativity. It's the lone ice cream cone of black hole diagrams. So what if we forget the real world and imagine an ideal black hole with an infinite past, leaving behind collapsing stars and everything else? What's the black hole analog of the full mathematical cone? It might look like a simple extension of our original Penrose diagram, but its physics is a little upside down. Region 1 is still our regular universe, and Region 2 is still a black hole with an inevitable future singularity. But the math also describes something inverse in Region 3. Instead of a future singularity, Region 3 has a singularity in its past. Drawing light rays at 45-degree angles, you see it's straightforward for light to leave Region 3, but it can never enter. This region is exactly what we'd call a white hole, the spacetime analog of a traffic cone. But that's not all. Beyond the white hole is a patch labeled Region 4, with the same connections to the black and white holes as the regular universe. This patch is a parallel universe, entirely disconnected from Region 1, since even light cannot travel between them. The upshot is the same mathematical equation describing the regular universe and black hole also describes the parallel universe and white hole. This doesn't mean every black hole comes attached to a white hole. Just like with cones, the real universe can contain chopped-up pieces of the full solution. But it does mean even if white holes are less common than black holes, or if none are connected to our universe, they're equally consistent with physics laws. In our analogy, if ice cream cones remain popular, while traffic cones become hard to produce and phased out, that doesn't make traffic cones any less real. This is roughly white holes' status today. The concept makes perfect sense, but any white holes existing in the past might have been unstable and phased out. If you wonder if more stable white holes escaped our sight, you're not alone. Stick around for discussing the tiniest possible white holes shortly. But first, buckle up, because Penrose diagrams describe more than white holes. We're about to go to a new level of warped spacetime into wormholes and parallel universes. The no-hair theorem says a black hole can have up to 3 intrinsic properties: mass, charge, and spin. The Penrose diagram shown describe the simplest kind, electrically neutral and stationary. Diagrams for charged or spinning black holes are more complicated and exciting, completely altering our understanding of singularities and giving rise to new fascinating spacetime regions. Look at the Penrose diagram for a spinning black hole. Instead of 4 distinct regions, there are now 8 types repeating in an infinite pattern of universes. Regions 1 through 4 are the same. Regular universe, black hole, white hole, parallel universe. But with spin, the black hole's geometry no longer has an unavoidable future singularity, and the white hole similarly loses its past singularity. So what happens after crossing a spinning black hole's event horizon? At first, you're drawn toward the center as expected, but eventually, you cross a threshold called the inner horizon, beyond which spacetime geometry unwraps and lets you stop falling deeper. In these innermost regions, marked 5 and 7, you can float freely toward or away from the center. You could even touch the singularity if you wanted, though it's not recommended. Here in these innermost regions of curved, rotating spacetime, you are officially in a wormhole. If not permanently separated from everyone in Region 1, this would be the perfect time to brag about your wild spacetime adventures. You also face a fork in the road. One option is to keep moving inward and go around the singularity, which for spinning black holes is ring-shaped, not a point. This path takes you to Region 6 or 8. But it's possible this path's existence is a flaw in general relativity's predictions rather than reality, because going even a single loop around the singularity can lead to causal paradoxes where you visit your own past. A safer bet is to turn around and move outward, crossing back into the inner horizon you just left. This takes you into Region 3, a white hole, carrying you out to a brand new universe similar to the one you started in, but sadly without friends or family waiting. By the time you get there, your old universe will have experienced an infinite amount of time. You'd be living in a whole new definition of the future. Okay, let's step back into reality. As fun as that theoretical wormhole journey was, you probably couldn't survive it in practice. And honestly, the wormhole itself might collapse once you disturbed its spacetime. So how much of this mathematical structure can we expect in the real world? Spinning black holes with event horizons appear everywhere, but what goes on inside is largely unknown. 2 main reasons real black hole physics might differ from the Penrose diagram's predictions. First, when black holes form from turbulent collapse of massive stars, some assumptions making the diagram are violated, like the black hole existing forever, or the universe being perfectly symmetric without random infalling humans. Second, general relativity used to construct the diagram might only be approximately correct, breaking down near the singularity where curvature is most extreme. So there's a good chance some diagram predictions, especially problematic ones involving singularities and time travel paradoxes, aren't real features of highly curved spacetime. But white holes' existence is more open, leaving room for speculation about how they might form and if they leave observational footprints. One hypothesis gaining traction is that a white hole is born whenever a black hole dies. This isn't magical reincarnation. It's a genuine attempt to understand black holes' full life cycle with mathematical backing. Even an isolated black hole in empty space continuously emits particles called Hawking radiation, causing gradual shrinkage and mass loss over time. Once the black hole reaches the super tiny Planck mass, about 20 micrograms, we can't predict its future without a full theory of quantum gravity. This is where loop quantum gravity comes in, a proposed link between gravity and quantum mechanics where space is made of discrete loops. In short, loop quantum gravity equations predict instead of shrinking smaller than the Planck mass, such a tiny black hole is more likely to quantum tunnel into a white hole, spewing its contents back into the universe over time. Incredibly, even though this white hole will be similarly small and light, it can contain enormous entropy because its interior geometry stretches into a thin tube with extremely large volume. This entropy store could open a pathway for information falling into a black hole to be recovered in the distant future, solving a decades-long problem known as the information paradox. As the white hole releases this information, it slowly fades from existence. Space-time around it loses curvature, and its life cycle closes. In general relativity, our universe is predicted to have had a singularity in its past, 14 billion years ago at the Big Bang. In this way, the universe is like an uncharged, stationary white hole. But if loop quantum gravity says white holes can be born when black holes collapse, could the same be true for our universe's creation? Could our expanding universe have been born from the ashes of an older, contracting spacetime? As crazy as it seems, loop quantum gravity says that may well be the case. So perhaps white holes as a concept aren't so far-fetched. Maybe it's time to start believing in white holes because, in a way, maybe we were in one. So white holes could exist in the real world, even if we haven't definitively observed one yet. But another part of the Penrose diagram might have raised an eyebrow. The diagram referenced parallel universes without issue, but that's a big claim. Could entire universes, inaccessible to ours yet running alongside us, just out of reach, actually exist? There are logical reasons to believe so, but before that, we need to turn to a baffling cosmic mystery and the worst prediction in physics ever. It starts with a deceptively simple question: why is our universe expanding? One of the first things learned in physics is gravity is an attractive force between two objects, proportional to their masses. Gravity keeps planets orbiting the sun, stars grouped in the Milky Way, and galaxies attracting to form clusters. But zooming out further, this gravitational attraction begins acting in reverse, causing galaxy clusters to accelerate away from each other. What's going on? Einstein's general relativity gives a lens to understand this strange behavior. In general relativity, space isn't just a background for movement. Space itself can stretch, warp, and evolve over time. Einstein showed in this framework, gravity is no longer a force, but a distortion of an object's inertial path in dynamic spacetime. For example, when a planet orbits the sun, in Einstein's description, it's merely following a straight-line path in curved space. This means what we observe as a repulsive force between galaxy clusters should be thought of as accelerated stretching of space between them. But what could cause space expansion to accelerate on the largest scales? To answer, we need to know what causes spacetime to stretch and warp. In Newton's gravity, all objects with mass exert a gravitational pull, and in general relativity, all objects with mass curve spacetime around them. But Einstein showed, besides mass, any form of energy or pressure also influences spacetime dynamics. Energy density is how much energy is within a given volume, and in our universe has always been positive. Pressure is how much force over an area the contents of that space push into the rest of the universe. For objects so far apart, this pressure value hovers just above zero on a cosmic scale. When these values are cumulatively positive, their influence causes space around them to contract, essentially creating gravity by decelerating space stretching. However, conceivably, if you could set values so pressure was negative and greater than positive energy density, the minus sign would flip everything, accelerating space stretching. Effectively, you'd get a volume of space filled with anti-gravity, a dark energy. It's tricky visualizing anything with truly negative pressure. How can you have less than 0 atoms in a patch of space? But atoms aren't the only things exerting pressure. Pressure is simply force applied across an area. Fields can also apply forces, like a magnetic field pulling iron toward a magnet or two magnets pushing apart. If dark energy were a field pushing away everything, it would match what we see the universe doing. vacuum itself having dark energy enough to slowly, gently push the universe apart. Scientists have thought a lot about dark energy, figuring out what its combined energy density and pressure needed to be to create the observed spatial expansion rate. It's around 10 to the power of -9 in SI units, a very small number, which is why we don't notice it on Earth, only on grand cosmological scales. This is good news because if the number were much higher or lower, things would get very bad for our chance of existing. Let's sketch the universe's history quickly. Here's the full history from just after the Big Bang to the present. This is the dark energy density measured by astronomers. Scientists believe its negative pressure has kept this density roughly constant for billions of years, though new evidence suggests dark energy may be weakening over time. For our purposes, keeping it consistent doesn't change the point. This is ordinary matter density in the universe, with little to no pressure. Density decreases over time because space expansion dilutes matter. Finally, this is radiation density, including photons and other extremely light particles. Radiation's positive pressure makes it dilute away even faster than ordinary matter. Early on, for a very short period, there were no atoms. Quickly, protons and neutrons fused to create the first atomic nuclei. Shortly after, matter became the dominant energy form. The universe cooled enough for nuclei to attract electrons, forming the first hydrogen and helium atoms. These atoms were building blocks for the first stars, pulled together by gravity to form the first galaxies and clusters. Only later did dark energy take over, triggering accelerated expansion and preventing larger structures. But what if energy density were larger? Consider if dark energy's pushing force were stronger. It could have halted early galaxy formation, pushing stars apart more powerfully than their gravity could pull them together. A bit larger and star formation would have been much more difficult. If dark energy density were large enough, we'd hardly have any atoms or nuclei produced. So that's what could have been. What should it have been? Using clever math and quantum field theory principles, scientists attempted to predict dark energy's energy density. Their result was larger than what we see in nature. How much larger? Their value came in at an astounding 10 to the power of 45 joules per cubic meter. Where does that fall on this graph? It's literally off the charts. If correct, the universe today would have no structure, no features, no life. It would be a giant void filled only with dark energy. If dark energy density were -10 to the 45 joules per cubic meter, the universe's fate would be no more promising, forced to rapidly collapse in a big crunch. So here lies the mystery. Why is dark energy density so much lower than predicted, at the very level needed for life? Scientists attempted to account for their number being so far off by hypothesizing undiscovered particles with positive energy and negative pressure that even out the math, bringing dark energy density back towards zero. Perhaps there's a massive negative potential energy source, a cosmic stretched spring reigning in rampant energy. Or quantum field theory is fundamentally wrong, but since much evidence supports quantum field theory, it seems imprudent to discard it. Instead, we contemplate this cosmic coincidence. What were the odds dark energy density would be so low when predicted so high? That this great universal balancing act occurred so we weren't torn apart or crushed into a singularity. Without it being so low, we wouldn't exist. Our atoms would never have come together, torn apart by surging, expanding space. According to predictions, we got very lucky. This coincidence happened so the universe could produce life. So was it a coincidence? Of course, there are different explanations for this dark energy density problem, often called the cosmological constant problem. Those of a religious mindset point to intelligent design, that a god or advanced being set dark energy density just right for life. This idea doesn't sit well with everyone. A godlike being's existence is difficult to prove or disprove, and faith isn't science. For many scientists, a different answer was needed. That answer came as multiverses. Go back to 1987, when dark energy density's precise value wasn't yet measured, but it was clear it was extremely small or zero since we existed. That year, physicist Steven Weinberg published a paper connecting the universe's fortuitously low dark energy density with the anthropic principle. Essentially, the only universes we can evaluate probabilities for are those meeting the right conditions to produce us. If the universe hadn't rolled such an unlikely dice roll, there would be no us to say whether things were more or less probable. If it takes a massively unlikely roll to produce humans, a universe where that roll happened is the only one we could possibly see. Weinberg could be more specific. He was confident the threshold of dark energy density for forming life would be no lower than for forming galaxies. By the time galaxies formed, you'd probably cross the threshold for life too. After all, how else could life arise without stars and galaxies providing complex building blocks and energy? At publication, observations of an extremely old, distant quasar-indicated galaxies began forming just 1 billion years after the Big Bang. Weinberg used this to calculate forming these ancient galaxies required dark energy density smaller than around 10 to the power of -7 joules per cubic meter. Assuming galaxies necessary for life, the threshold dark energy density for life was less than or equal to this value while not so low as to be negative. Weinberg initially reasoned, if dark energy density was significantly smaller than this, something else must explain its smallness. As we now know, real dark energy density is closer to 10 to the power of -9, not too far off from Weinberg's threshold of 10 to the power of -7. In short, life and dark energy density correlate surprisingly well. Of course, this ignores one vital point. Just because we can see universes where we exist doesn't guarantee we should exist. We could have just not existed. The odds of the cosmological constant being at its recorded level are incredibly unlikely. Could various contributions to dark energy density have canceled out to a life-compatible value by chance? Probably not. Imagine generating 3 random real numbers between -1 and 1, adding them, and hoping the sum's magnitude is at most 0.000000, and so on, with 55 zeros. It sounds impossible, but what if we had more than one try? What if we could generate those numbers over and over until we got lucky? It might take something like 10 to the power of 56 tries, but given enough time, unlikely cancellation becomes inevitable. We can use the same logic to potentially explain why dark energy density is so bizarrely small. Instead of one universe, imagine a vast multiverse, each universe having a different, random dark energy density value. Only a tiny fraction would have a density small enough for life, but that's exactly where we humans would expect to find ourselves. This explanation requires no coincidences, fine-tuning, or intelligent design, just many different universes. Alone, the multiverse idea is too vague for good scientific theory. What kind of multiverse? How do they exist? Fortunately, physicists describe a few different concepts. First, a multiverse separated by time. If familiar with Big Bang and Big Crunch, it's often believed creation and destruction is an eternally repeating process, new universes arising each time. If underlying numbers differ each iteration, like dark energy density changing from universe to universe, then with enough Big Bangs and crunches, you could inevitably get a universe with dark energy density like ours. There are assumptions, as we don't know if the universe contracts into a big crunch yet. But if it does and universe rules differ each iteration, this is a viable multiverse model. A second multiverse described by physicists, though personally iffier, is a multiverse separated by space. While physics laws seem consistent across all space we see, realms beyond our sight exist, sections accelerating away so fast we'll never see light from them. It's conceivably possible rules in these parts differ from ours. If so, we're essentially in another multiverse. This model is less satisfying because calling a farther part of our universe a different universe just because we can't see it feels strange, and there's no evidence physics laws differ across space. This seems the least likely multiverse. Finally, modern physics describes a third type, disconnected from our spacetime entirely. In the many worlds interpretation of quantum mechanics, every macroscopic interaction or measurement of a quantum state causes the universe's wave function to branch into multiple non-interacting parts. If you've heard of Schrödinger's cat, imagine the universe splitting into one where the cat is alive and one where dead. With each interaction, total universes grow exponentially, the quantum multiverse becoming richer and more diverse. We still don't know if this branching is correct, but it's arguably simplest and consistent with all experimental data. We have no proof it doesn't exist that way. If correct, it would add a new layer of complexity to our multiverse understanding. Multiverses remove the need for massive coincidences or intelligent design explaining our presence. However, are they real? Unfortunately, the answer is unsatisfying. We don't know. While differing multiverses help solve the cosmological constant problem, we have no evidence beyond offering an explanation for that coincidence. We have no proof physics laws change across space, time, or quantum universes. If other universes exist, they might have exactly the same laws and dark energy density values, putting us back at the same problem. How are we here when galaxy existence odds are 10 to the power of 56 to 1? Or worse, dark energy density is 10 to the power of 56 to 10 to the power of 120 times smaller than predicted. Getting proof will be difficult. We'd need to survive a big crunch, pass into a part of the universe so far light can't travel back, or enter a different quantum universe somehow. All seem impossible or very difficult, potentially a one-way trip. This might be as unprovable as God's existence. So, you're free to believe whichever you find most comforting, or wait for a better answer. Ultimately, whether parallel universes, wormholes, white holes, or gravastars, science's theoretical landscape brims with possibilities. Remember, there's sound precedent for hypotheticals becoming realities. Black holes, Neptune, antimatter, cosmic background radiation were all found in theory before practice. We live in an age where our mind's eye frequently outpaces physical vision, where math and equations leave telescopes or detectors in the dust. It's marvelous we live in a universe founded on logical principles allowing such deductions, where we can Sherlock Holmes reality. Rules are so consistent that once understood fundamentally, the rest of the universe naturally arises. I love the order and wonders possible because of it. So could these things be real? Yes, if we've understood theory correctly. And if we haven't, then I can't wait to see what strange, jaw-dropping phenomena science predicts next as understanding improves. And of course, the day when what we imagine is no longer imaginary, when we spot real-life counterparts waiting among the stars. If you enjoyed this journey through cosmic possibilities, help others discover it by liking this video. Share it with friends who love pondering the universe's mysteries, and subscribe for more explorations into the wonders of space and science. Your support helps keep the curiosity alive.